Okay, so this is the microprocessor. This is digital electronics, and we're going to work on doing the blinking LED lab. Okay, so yeah, what we're going to do is we're going to pull up the Quartus version 11 software. And specifically, what we're going to open up is your schematic-based tutorial. And if you, like I said, if you don't have it saved, then you can quickly go draw it. It's just a few little gates. You don't have to worry too much about the pin locations right now, even though eventually we will need those. And I believe the Getting Started tutorial is under the Help menu if you need to have more information on it. And that thing is not working. Which also should be under the Altera and Quartus 2 Web Edition and the Help. Looks like I've got some problems with that today. Don't worry about that. Okay, what are we going to do today? We're going to add, remember last week we added some, last week we did the multi-sim simulation. The week before that we did a little block of Verilog Code. Okay, so this week we're going to do another block of Verilog Code. It's going to be a little bit different. And if you see my block, I have it's a counter. And what the counter is going to do is it's going to use the 27 megahertz clock. And 27 megahertz, that's 27 million times a second. And so in order to get a light to blink, we're going to have to divide that down into about the 1 second or 1.5 second range in order to see the light blink. Because if you blink the LED at 27 megahertz, it's just going to be so fast you're not going to be able to tell. It's just going to look dimmer. It's not going to look like full strength. And the reason we're going to do this is we're going to use this counter to make a motor driver. But first we're going to take baby steps to get there. So if you double click on this, I'll show you what's inside of it. This is my counter. Okay, so the way that the Verilog code works is you use the module command to create a new module, a new component, you could say. And we can call it whatever you want to call it. In this case, I called it binary counter. Okay. Then we use the parameter command. It's kind of like creating a constant. If you've ever written any type of programming language code, parameter is kind of like making a constant. So we're going to say width equals to 64, and this is going to set eventually it's going to set the width of the counter. It's going to be a 64-bit counter. Now the good thing about doing it this way is if you ever want to change the width of your counter, all you have to do is change this one parameter. And another good thing about this is it actually passes that parameter up to the symbol level. So if you go look at the symbol, see here that you have a little box here that says parameter. You guys, is that better? You have a little box here that says parameter, and then you can go in there and you can actually change the value of that without having to go to your code. You can do it on the schematic if you do it that way. And of course, you don't really have to do any of that. If you wanted to, you could just come in here and code the width of that counter to just be a number 64. But if you do it this way, then it'll allow you to pass it from the schematic into the Verilog code. Then the next thing we're going to do inside of the module. Now, note that the parameter, this part of the code, is extra. This doesn't really have to be there. Typically, when we write a code, the basic structure is you do module, the name of the module, you do parentheses, and then in parentheses with a semicolon. And then inside of these parentheses, you put your inputs and your outputs. So in this case, we're going to do input. We want to have a clock, an enable, and a reset. Clock, enable, and reset. Right? So remember, this symbol here is going to be generated from this code, not the other way around. So when you're putting clock, enable, and reset, when you generate your symbol based off this, that's going to create these inputs. Okay? So you can name them whatever you want. You can write out the entire word, clock, C-L-O-C-K. You can use EN for enable. It doesn't really matter because as long as you know what to connect them to on the schematic. Reset. Now what we're going to do is we're going to use this little thing that we created. Remember last week we mapped these to certain push button switches on the DE0 board, and when you push the push button switch, it toggles this output either to 0 or 1. It's not really important what it is, but the idea is you can use this to reset your clock. So when you push the button, it should reset your counter. Let's go back to this. Now we also want to have an output, so you just type the word output, then space. Reg means that we're going to have an output that has memory, that has the ability to store values. So register, I don't know if you guys have talked about registers yet. I think that's the next section you guys are going to talk about, according to Ron. You're going to talk about registers and latches. But a register is an element inside of a digital block that has memory, has ability to retain its value. These registers, for example, if you load a 1 into a register, it can remember that value for a long time. Or if you load a 0. And so that's the way this counter is going to be. The counter basically remembers a certain set of values and then it increments that value. But it has the ability to store and hold that value. So we're going to let this be a register. Where these inputs are just wires, they come straight in and you connect whatever you want to connect. They don't remember, they don't have ability to remember anything. It's just a wire. Now, so this output is, instead of, if we wanted this output count value to be just one single bit, then we wouldn't have to put this code there at all. But we actually want this counter to be multiple bits. We call that a bus. So we want to have a string of zeros and ones. In fact, we want to be able to count up to a 64-bit number. So that's why we use the word width here is getting replaced with this parameter. Now normally we would do something like this. 63 down to 0. Okay? That would create a 64-bit counter. If we wanted to have a 7-bit counter, we could go 7 down to 0. Now, the number on the left defines what the most significant bit is, if you look to the left. Because the most significant bit is going to be here, the least significant bit is going to be over here. So, if you reverse this, let's see what happens if you reverse this. If I put 0 to 7. Well, what that says is that bit 0 is going to be the most significant bit because it's on the left. And then the 7 would be the least significant bit. We don't really want that, right? It would work, but it would be confusing because normally we want to have what? 0. Bit 0 would be your least significant bit. It makes more sense, right? Agreed? Bit 0 would be your least significant. So if you want 0 to be your least, but it's perfectly valid to do this. You can have 0 be your most significant bit. You're just going to have to remember when you start breaking the bits out and grabbing those, you're going to have to remember that everything's reversed. But in this case, we're going to make it easy on ourselves. We're going to say 7 down to 0. Now, but think about this for a minute. We have a 27 megahertz clock. And we're going to count to what if we had an 8-bit counter? Yeah, we're going to count to 255. 0 to 255, right? let's bring up. You can bring up your calculator. If you bring up your calculator and go to programmer mode, it gives you this binary calculator. Put in 11111111. That's a what? That's a 4-bit. That's an 8-bit number, right? Mm-hmm. Agreed? This calculator here can do up to 64 bits. You see here 0 through 63. Okay? Mm-hmm. Now, if we convert this to decimal, it says 255. So, 255. Now, we have a 27 megahertz clock. That's 27 million. Now we're going to divide that by 256. 256. Oh. Let's go back to the standard calculator. 27,000 million divided by 256. That's going to reduce our frequency to 105,468 per second, pulses per second. Are you going to be able to see that? No, not going to be able to see it. Okay, so the question is, how big of a counter do we need to get this down to one pulse per second? Yeah, we need a number to be pretty close to what our clock is, right? 27 million. Okay. So what we can do is we can go, let's see, scientific calculator. Now, 2 raised to the, let's do 8. 2 to the 8 is 256. We just did that one. That's how you use the exponent. 2 to the 8. Let's do, what if we do 2 raised to the, 16? That would be a 16-bit counter. 2 to the 16 would give us 65,000. Still not big enough. How about 2 to the 20? That's about 1 million. 2 to the 20. So a 20-bit counter would be a million.
So about 27 times a second.
So that would still be too fast. So if we do 2 to the 64? Oh, that's too big. That's too big.
2 to the 8. 2 to the 42.
2 to the 45. It's still too big. 2 to the 20? Oh, we already did 20. Let's just increase it by, so 20, well, let's go back to that. 2 to the 20. Okay, that's a million. Now, every time we go up in bits, then we double it. Okay, so so now we can just start multiplying by 2. So if we multiply by 2, that's 2 million. That would be 21 bits times 2. That's 4 million, right? That's 22 bits times 2. That's 8 million. That's 23 times 2. 16 times 2. 33. So what size is that? 20?
That's going to be
24?
1 seconds.
Okay. So 24. So this counter is probably too big. But we're going to leave it 64 because that's the way we had it. But if you look over here, notice what I changed it to over here, 24. So let's leave it 64. Now the reason I say that is because it's going to, this parameter you can change it. We're just going to set it 64 is just the default number. Now when we create it, we come over here, we change it to 24 right over there. You see what I'm doing? Yeah. Because when I first built the counter, I didn't know how big it needed to be, so I just made a really big counter, like ridiculously large. And you can change it over here. And actually, 24 turned out to be pretty good, which is exactly what we just found it would be. So what you can do is you can just play around with it and screw with it and do the trial by error method, or you can try to calculate it. Okay, so what we determined is we really need maybe like a 24-bit counter. So that would be 23 down to 0. Okay? But what we're going to do now, but notice this for a minute. This number, this 23 really is what? It's 24 minus 1. It's however big you want the counter minus 1, right? So what we're going to do is we're going to use this parameter thing. We're just going to say, let's just call this a width. We'll just call this width. And we'll subtract 1 from it. Now, anytime we want to change the width, we'll just change it on the schematic. We don't have to worry about changing it in the code. So that's what the parameter thing is. And we're going to call that output, we're going to call it count. Okay, so this is, we have count right here. Count width minus 1 down to 0. And we can change that width right here by clicking that box. Now we get into the actual meat of the code. The only thing we've done so far is we've created a module or a component with a name and binary counter. We've created 3 inputs. We've created 1 output with the and the output is actually a bus. So it's not a single bit, it's a bus. And we have the ability to change the width of that bus through the width parameter. Okay? That's all we've done so far. So really the only thing we've done is we've created this symbol, we've created the inputs, we created output, and we've created this parameter box that we can click on and change the width of that right there. But right now we have basically a blank box inside there. There's nothing in there. We have to tell it what we want it to do. So this is how we tell it what to do. This is Verilog. And anybody interested in learning Verilog, this is a really good book. You can... my boss at Texas Instruments bought us each a copy of this when we started working. You know, most people learn Verilog on their own. That's just the way it works. Most schools don't really teach Verilog. They just tell you that it exists, and then they expect you to learn on your own. Because really, it's just, how do you learn something? You just do it. You know, Verilog is just like you just do it language. You get in there, you start playing around with it. Everyone's got a computer. Everyone can download software for free and just screw around with it. You don't need any expensive equipment to do this. You just download it and start working on it. But I'm giving you today the basics of how it works. So what we're going to want to do is we're going to do a counter that always counts.
Is this recording?
No, it's recording right here. It's always counting. So what we use is, we don't use the initial statement, we use the always statement. Okay? The always statement says always at positive clock or negative edge of the reset. You can kind of leave that out. The most important part of this code is always at positive edge of clock. And the negative edge of reset is not as critical, and some people actually leave that out. But every time the positive edge of the clock comes, then it's going to increment a value. It's going to increment because we're going to tell it to, if the reset is a 1. You have to think of, in digital logic, if statements execute if they're true. So you have an if statement here. It says begin and if. So if this inside the parentheses is true, and what's the definition of true in digital? 1. Definition of true is 1. False is 0. So what that means is if reset is a 1, right, then this code below will get executed. If it's a 0, it's going to skip down to else. Okay, that's the way it works. Now you could say if reset equals 1, and that would actually be the exact same thing, no difference. We could also say if reset equals 0. That would be different, because now this would only execute if reset was 0. But here we're saying we want the count to be cleared. We want the count value to go to 0 if reset's 1. That makes sense, right? If your reset signal goes high, clear the counter, right? Alternatively, you could say, I could reset the counter to 1 or 100. You could reset it to whatever you want. But in this case, we want to reset it to 0. And the way you assign values to registers, anything with the name register, which the count is a register, see there? You have to use the assignment statement, not equals. Equals is what you use to test something, to compare something. If you say, if reset's equal to 1, you can just use the equal sign. But if you're actually assigning a value, what this is saying is we want 0 to get put into that register. It's different. It's an assignment statement. Okay? We use equal to compare two things. We want to compare reset with reset equals 1, so you're comparing reset with 1. If they're equal, then it gives a value of 1, a true. If they're not, then it gives you a value of false. But in this case, we want to put 0 into the count register if this is true. If it's not true, then we're going to go down to the next statement. If this is not true, it executes the next one. Else if. And if this one's not true, you could have another else if, and at the end of that you could have else. So it would be if, else if, else if, else if. Or, I'm sorry, else. Else would be your last one, if you wanted to have one. But in this case, we only have two. If, and then else if. If this one's not true, then the other one's going to take over. It says else if. Now, it's possible that neither one of them are true. If neither one of them are true, then nothing happens. It just means that the count value stays the same that it was. There's no change to the count value. So two things are either going to happen. Either the count value is going to go to 0, the count value is going to increment to 1, or nothing's going to happen. But in this case, the next else statement says else if enables equal to 1. Now we have this one tick B1, and really this is the same thing. If enables equal to 1, then count equals count plus 1. Now this one tick B1, what that means is, I'm sorry, one tick B1. That's just another way to write a 1. It's a really confusing way to write a 1. This just says that this 1 is going to be 1 bit wide. It's going to be in binary.
So double equals means what is double equal mean?
But it's the same as that. So we can just leave it like that. I don't want to make it too confusing right now. Enable equals 1. If enable is equal to 1, then you're going to take whatever value is in count, increment it, and then you're going to stuff that value into count. Okay? So count, increment count, stuff that value into count. What that's essentially going to do is it's going to increment the counter. Yeah. Yeah, in this case, when you have a inside your parameters, inside your parentheses, when you're doing a comparison in Verilog, you need to use the double equal signs. Now notice up here when we did a parameter, use the equal sign. We used a single equal sign to set a parameter equal to a value. When we do a comparison, we use the double equal sign. And when we do an assignment, we use an equal sign with a less than symbol. So, yeah. It's not so simple as just using equal sign equals. The main thing to remember here is, another thing here is you don't really have to do this, right? What would this do? What if we did this? Wouldn't that be the same thing? It's the same thing. If enable, if this is true, right? If it's 1, So there's not just one way to write Verilog. I mean, Verilog code looks different depending on who writes it. It doesn't. There's many different ways to do this same function actually. So don't think that this solution is unique. By the way, the Carnot maps that you guys worked on, there's not always a unique solution to those either. In other words, you guys are used to, oh, there's always one answer, right? Well, when you start to do design work, there could be 100 different answers, and two different designers their code's going to look completely different, and both are going to work, possibly. One may work better than the other. One may be more reliable. So how you code and things like that may matter. But in this case, this is going to be equivalent. So you get up here. If we wanted to change this, if we wanted the count to actually increment when enable was low, that would be considered what? Active low logic, right? If we wanted to make this active low logic, we could say if enable is equal to 0. That would mean enable now would be active low, right? When enable was low, now it would increment the counter. But if I did that, what I would do is I would actually rename enable to something like enable _n or enable tilde. I would rename the signal to indicate that it's active low logic. That's what most designers do. Like a lot of people would do, some people would do a pound there, or they would do a tilde to let people know. When they name the signal, they would just let them know that it's active low logic. But then, of course, you just compile. You compile your code. Let's see here. Click this little analyze current file. Okay, you click the analyze current file, which is really the little run symbol. It says successful, and if it's not successful, to give you a warning. And then, based on this code, we do the same thing we did last week. File. Now with this code up, you have to make sure this is up. You do file, create symbol for current file, create symbol file was successful, and then you go place the part. You click the part button. You go to project, binary counter, okay. It created the part for you. Now, since we had, notice up here, what do we get? It says 64, right? Because we added this parameter thing, then that's why we got this parameter box. If you don't add the parameter, you don't get a parameter box. But now that we have this, we can... the reason I have this box is because when I was making this counter, I didn't know how big. I didn't take the time to calculate what the value was. I just said, I'm just going to make a big counter. And I just did by trial and error. I kept changing the count value manually because I just got in a hurry. And then after a while, I'm sick of recompiling my code every time. Every time you change the value, you had to recompile your code, right? Well, I said, I'm sick of that. I'm just going to write a really big counter, and then I'm just going to change it here. So I don't have to keep recompiling my codes, because if I do that, see, I'm done. I just changed the value of my counter. I don't have to recompile it. So now you can wire it up. Now what are we going to do? We're going to wire this up. The reset here is going to go to reset, enable. Just pull the enable high. We're always going to have it enabled. You could alternatively, you could connect this somewhere. But really the enable would be used for if you had a big system, you would have enables everywhere in the entire system. And anytime you wanted to shut the entire system down, you could just pull enable low. And we used to call that like a master reset type of a signal. Or a master enable and master reset. And then we're going to take the clock and we're going to connect it to, you guys have a clock. If you look in your lab manuals, you have a clock. Go to the if you go to your DE0 board, there's a section on clocks. Somewhere. Okay, page 28 on the back. Page 28. I think the one I designed this one for the DE1 board, and it had a 27 megahertz clock. You guys actually have two 50 megahertz clocks, so yours is going to be. So what you have to do is make sure that when you do your clock, make sure you call it the correct name. So I'm going to go to assignments, and I'm going to say import assignments. Okay, and then I'm going to go to DE0 assignments. I'm going to pull those in. Now if I go to my assignment editor, look around and see if you can find your clock. See there you have a signal called clock 50. Good?
Yeah.
So all you're going to do is, since we already have those, you just need to name your signal the same name as that. You actually have two 50 megahertz clocks. We call it clock underscore 50, clock underscore 50 underscore 2. So there's actually two separate clock inputs on your board. So what we can do here is we can, if you name this input clock underscore 50, then it'll automatically pull in the correct assignment for you when you do your compile.
It has to be lowercase.
Clock 50. I think last week we determined that it doesn't, but one year when I was working on it, it did have to be, so they may have changed it. But either way, lowercase or uppercase. Now if I hit compile here, let's see what happens.
Your output wasn't connected.
Actually, I believe if I go back here now, it should be working. See there, it got assigned G21. If you check in your book, G21. See right there? So it just automatically assigned it. Full compilation was successful. Now, if I had a DE, if someone wants to borrow the board, you guys can go ahead and get started on it. I'll download it and then I'll demonstrate it to you guys, and then I have to run out. I have to leave because my wife has to come teach, and I have to go home and watch the kids for her. But my kids are sick today.
How'd you get that CNT23?
Oh yeah. When you create this part, you have to name this, and when I named it, count 23 down to 0. How do you do that? Well, what you do is you click this little bus. I think this little tool right there. Do you see that tool there? See right here, you have the node tool. This is for a single wire, and this is you have the bus tool. The bus tool is for multi wires. So if you click the bus tool right there, it gives you a. Notice that the wire is thicker than the other ones. You notice that? And it's
Gotta go to property.
yeah. Then you have to just go to the properties, and you'll just have to name it. You can name it whatever you want. It doesn't really matter. I just named it CNT. But you have to make sure that it's the right width. So we did 23 down, 23 to 0. Now it's different here. You have to put ... 0. And that's because this tool, the block diagram editor, is a different tool than Verilog. It's not the same. They're two completely different tools. This block diagram editor is designed by Altera. Verilog is an industry standard code. It's actually an IEEE standard code. So, two different manufacturers, I guess you could think of it like that way. Now, so now the next question is, how do I get this output to pulse one single LED? Well, obviously, I don't need 24 bits, right? I just need 1 bit. So what you do is you grab the most significant bit. Why? Because that most significant bit, think about the mancula, when we were counting with mancula beads, you put the bit in on the least significant bit, and it filters through to the upper bit, right? But it's going to take a long time for that to flip. So this 23rd bit here is going to be the slowest bit. It's going to toggle really slow. Well, these other bits down here are going to be flipping really fast.
You could make another output, something else.
Yeah, so we're connecting this most significant bit to the LED. This is going to be your LED.
And you could do another output, like, so you had 2 light splashes.
Yeah, you could. Yeah, you could do bit 2022, and then you put that to an LED, and it would blink faster, and the other one would blink slower. Yeah, you can do that. Yeah.
We don't have a pulse on ours. You labeled that pulse and it labeled PG21.
Oh, you can call it whatever you want. No, I would call this LED G0 or something. You can call this
Yeah, I already had it now.
LED G. Well, you can call LED G2 or whatever.
Right, okay.
It doesn't matter. LED G5. Is that what we're gonna do? Okay, let's call it LED G5. But just make sure that it maps to something that's on your table here. LED G5. Right
There
there.
it goes. Now it's like
Let's see. What are we going to call this? P. Actually, if I'm going to demonstrate this, I'm going to have to.
They use switches.
I'm going to call this button.
We're doing buttons.
Button 1. Button 0. Button 1. Clock 50. This is LED G0. There we go.
I had it working earlier. Simple circuit.
I'm gonna compile mine, and I'm gonna try to download it just to demonstrate it to you guys, and then I gotta head out the door. Actually, I don't even know if I have time to do that. Actually, but may not get time.
I can't get one file.
Oh, that was quick. Okay.
Yeah, mine.
Can I borrow someone's board just really quick?
I just didn't know.
Oh,
Box next to you.
oh, this one. Okay. Program.
Button 0 does something anyway.
Huh.
They got changes.
Oh, you know what? I don't think I have the. I don't have the driver loaded on my computer. Anyway, you guys can get it to work, right? I'm gonna have to set up the driver. I thought I had the driver on my computer.
Hey, mine's working.
You used it last time.
Yours working?
Mine's blinking and then
Oh yeah, his is working. Okay, I don't have to do it.
I hit the switches.
Good.
See, when I hit the switches and it does the same thing.
Do what? Oh yeah, let's put the code up there. Yeah, in fact, what I'm going to do is
The LED LED 5 is flashing, and then when I hit the button, it stops. It also lights LED G0.
Let's see here.
These are enabled.
You didn't have to put that on there.
Because I changed it to buttons.
As long as it was in there at once.
Wait, is this what it's supposed to be doing right here? Yeah.
Wait a minute. Wait just a minute. Okay. What I'm going to do is
So we can just go ahead and scroll down if they need to.
crap. There we go. I'm going to do a screen capture really quick. Screen capture. Print screen. Paint. Save Lab 10. We're going to call this blink LED. I'm gonna post this on Moodle really quick.
Yeah. Can't believe I actually got one working with no problem.
Yeah, you can write him off. Well, we've already written him off.
You written them off already?
Where did he go?
You know, both buttons are pressed, then it doesn't matter.
Blink LED Lab. And
Both of them enable see. But pushing both, it still blinks.
Yeah.
If I let one go, then
blink LED. There we go.
it blinks. You got literally just go line by line.
Okay.
Exactly what you need. Those kind of automatic.
Okay, I posted it on Moodle just in case you guys need it, and
Right.
I'll actually I'm gonna have to take this computer. So what I'm gonna have to do is put it on this computer.
You got somebody running over here.
Hey man, how's it going?
He might need me one day. You're not going to have anybody taking advanced PLCs
No,
or the maintenance classes. That's what I thought.
no, not this semester.
I didn't think so.
We'll have to get into it. Yeah, next semester.
That's next-
These guys will. This class will take it next year.
Next spring. Gotcha. Okay. I was going to double check because we're trying to schedule you for continuing education.
Yeah, we're good for this year. Let's see.
There it is.
This is it.
Yeah. Okay, good. So I gotta get out of here.